Good morning, honorable judges. Today we will present our research, What Can You Split and Draw? Our research utilizes three main fields to study drawability and develop layer drawability. Our research is based upon What Can You Draw by Frick and Peng, and we have consulted Professor Frick through email on our novel direction of layer drawability, which he appreciated. And these are the main results. We extended the definition of drawability and came up with the idea of layer drawability, which we will explain later. And this flowchart shows the theory flow and the connections between the dense theorems in our paper. We will start with our notations and motivations. We utilize the Minkowski sum to model the physical act of drawing, combining the step, which is the path of the brush, and the brush itself, and use the stroke. Then we have the illustration of drawability. Here, the definition shows how drawability can be rigorously described with topological tools with the alternation of exclusions and unions of strokes. This allows us to connect topology and drawability. For motivations, our first incentive is the collection of digital brushes being limited. Moreover, the original paper left a couple of directions for further research, with the last two being best reflected in the difference in definitions. Here, our brush is generalized, and for drawability, we have included the infinite case. The latter difference can be best illustrated with this S composed of infinite Ds. It can be proven that for any drawing sequence that draws S must be of infinite length. So S is still drawable according to our definition, but not theirs. And this better aligns with our intuition on drawability. And when we are given a drawing sequence, we could easily construct the final image. However, finding the existence of a drawing sequence sigma for a given figure S is not always trivial. For this, we developed three concepts: last strokes, hypothetical last strokes, and containment loops. The first one is the last strokes, whose inspiration is taken from the proof of lemma 8 of the original paper. And the term touching inspired us to formulate the notion of affecting, which is characterized by the change in all the neighborhoods of some points rather than simply touching. And the last strokes combine the notion of affecting with a third condition, which requires local equivalence with the final image. Yet, some drawable figures have boundary points at which every possible drawing sequence sigma yields the absence of a last stroke. The concern of the convergence of the image can be judged on the right. So, the accurate generalized statement of last strokes should be theorem 1, which states that a drawable figure will always have a sequence of strokes where every boundary point either has a last stroke or is affected by every stroke. And the second idea is the hypothetical last strokes, which is a set of brush translations with conditions, and is proven to be, in some sense, a set of minimal last strokes. Note that it is usually denoted by alpha. And the last idea is the containment loop, which is inspired by theorem 15 of the original paper, and formalizes the idea of figures having a contradiction in the order of strokes. And to illustrate the idea, we start from the simple notion of containment. Here, x1 associated with a chosen alpha covers x2. Then we say x1 contains x2 with alpha 1. And as an expansion, a containment loop, as the name suggests, is formed when we spot a loop of containment among multiple boundary points with chosen associated alphas. And now is the time to address the formal notion of describing drawing obstruction, which is the inheritance of containment loops. The definition is dense, but the main idea is if every combination of the associated alphas leads to the containment loops forming, implying that drawing obstructions are unavoidable, then we say that the selected boundary points inherit a containment loop. Foreseeing from the last slide, checking the inheritance of containment loops requires exponentially growing or infinite combinations of hypothetical last strokes. So, to retain a feasible research, we have to determine how many hypothetical last strokes a point has. The detailed classification of hypothetical last strokes can be found in our paper, but in short, under some conditions, X can only have 1 or 2 hypothetical last strokes depending on the curvature at X. And with the concepts ready, we present the core theorem of this section, theorem 3, an if and only if condition on drawability, with limitations. The forward direction is proven with theorem 2, which applies to any S about the necessity of drawability. And the backward direction is done with a construction proof, and the concept is the following. If containment is present, but not containment loops, then containment chains are present instead. And under the finite chain condition, we can find the beginnings of the chains. There, the points are not contained by any chosen hypothetical large rows. Hence, we can start drawing S from there. So we needed our ordering function, and we defined the ordering function rho, which returns 1 less than the length of the longest containment chain ending at a point. We are sorry that we made a typo in our paper. There should be a +1 here. And its supremum in the rho function guarantees the ordering, and its calculation is accessible in practical drawing. Then we can start drawing from the points whose rows are 0, and the points whose rows are 1, so on and so forth. And finally, we obtain S, and this concludes the proof sketch. Then we move on to layer drawability. Here, S is composed of a square and a triangle sharing a vertex. It is undrawable because of these 4 points inheriting a containment loop. But the square and the triangle themselves instead are drawable, and this inspires us to further classify undrawable figures. Hence, the natural follow-up question is, how can we optimize the number of layers that is decomposed as effectively such that the least of them are used? But the optimization is not trivial. So we associate it to graph theory, and we will demonstrate it with 3 infinitely spaced circles. The first essential step is to partition S into shorter arcs and construct a mapping between the arcs and vertices in the context of graph theory. For any pairs of vertices, they share an edge when their corresponding arcs embody a linked to containment loop, as demonstrated with U and V. Thus, the concept of layer drawability graph is established. Still, its true potential requires something to reveal it, which is graph coloring. By utilizing coloring algorithms in graph theory, if we assign layers to arcs according to how the colors are assigned to the corresponding vertices in this layer drawability graph, then each layer of arcs is highly evident to be drawable, contributing to finding the minimum of n. And Theorem 5 reveals a practical partition that secures the minimum of n. Before we present the proof sketch of it, several preparations are needed. Firstly, boundary points of S in H1S has only one hypothetical large stroke. It is the only domain of S applicable for analysis, and its rationale is explained before. The second concept is primitive points. Here, P and Q are primitive points because they share the same hypothetical large stroke. And actually, they carry another meaning. See here, these 2 arcs do not embody containment loops, but these 2 do. And this, the primitive points marks the instant when the containment loops are no longer embodied. And the last concept is the expanded and reduced scalar graphs. It reflects the change in layer drawability graph when a partition becomes finer. Vertices are expanded into the sets of descendants, and the chromatic number is decreased. Note that the absence in HAE carries over to G prime. And this is an example of an expanded and reduced color graph of G. And now we will present the proof sketch of Theorem 5. The idea is to merge P star and the hypothetical partition Q into Q prime and try to arrive at a contradiction. Here, the structure of Q prime is captured with the expanded and reduced color graph as prepared. And this is where the proof is inspiring. There are no fallacies present in the aspects of geometry or graph theory. It turns out that the contradiction roots exactly in the philosophy of P star. When one imagines a better partition, new primitive points appear and contradiction happens. This proof reveals the stunning beauty in the underlying linkage between geometry and graph theory. And if you would like to dig deeper, please refer to section 4.2. But there is a little caveat. That is, our graph only considers links to containment loops, but not longer ones. This loss of information is the reason why we cannot claim equality for Theorem 5. But such containment loops, of which minimum coloring is unaware, could actually easily be resolved by rearranging the colors while maintaining a minimum coloring. Even so, we suspect that it is way more difficult to prove than Theorem 5. Hence, we invite the judges to attempt on this conjecture. And finally, here are other theorems which cannot be detailed, which is Theorem 7 and Theorem 8. Please refer to our paper. And here is a case analysis on our school emblem, which is 3-layer drawable. And here is a recap on all our results, and that's all for our presentation. Thank you for listening, and please join us in the research of this field.